Bob Goldberg over there, and then Robbie.
Thanks, Steve. That was great. My question is, does it need to be mesenchymal stem cells to do this with skin fibroblasts?
Yeah, I'm trying to think back. We did do some with the skin fibroblast cells, and it worked just as well. So again, it's not a receptor mediated, so it's a pretty homogeneous across all the cells that we've tried. But we have tried with the skin fibroblast cells, with the pig skin fibroblast cells, and then we used them in the nuclear transfer procedure and produced some transgenic embryos and that was with the AAV system.
I had a similar question. I was wondering what your thoughts were on using muscle or other products muscle and
I think it should. Right. Yeah, I think it should be tried. We didn't try muscle cells, but I think it's a robust system to get the adenoviral vectors in.
Are there other questions for Steve Stice? If not, thanks, Steve. We'll move on to our next speaker, Pat Staten, who, since he's spoken before, doesn't need an introduction. And this time, we've done everything possible to not have a 30-minute computer malfunction delay.
It's not working. Yes. So I want to thank Steve for, I didn't realize how great that would be as a talk right before mine. I'm going to take a step back and talk a little bit more generally about how nucleic acids are currently delivered. But I'm going to focus on viral delivery methods. Yesterday in my talk, I tried to put protein delivery in the context of tissue regeneration strategies. And again, then just to quickly summarize, a lot of times what we're after is controlling events within the scaffold. But we always have to remember that when these go back in vivo, that there are also interfacing events that we have to control outside the scaffold. And so you really need to think about being able to control cell behavior within the scaffold as well as outside the scaffold. And so today I'd like to just add into the repertoire of methods that we can use to control behavior both within and without the scaffold, nucleic acid drugs. And again, these have been used and investigated to control cells as they come into the scaffold. They've been used to control cells, as Steve was just going over, even prior to the point in which they might be added to a delivery vehicle, a cell delivery vehicle. But you can also think about these, and I'll give you an example of how nucleic acids can be used to control events around the scaffold. And these, again, probably most prominently would be targeted toward the control of angiogenesis and the foreign body reaction. There are, for the most part, three general categories of nucleic acid drugs that are under development. The first is, in fact, genes, so that would fall under the category of gene therapy. The other two categories that are being investigated are antisense drugs, which are short pieces of synthetic DNA, modified DNA usually. And antisense therapy has kind of been a roller coaster, up and down, and people have very strong opinions about the likelihood of whether these are going to be a real therapeutic, but still under active investigation clinically and through several companies. The sort of new kid on the block that is taking all the headlines is siRNA, which arises from a recently discovered biological phenomenon. I'm always amazed still in biology that we can, still in this day and age, discover incredibly new biology. And RNA interference has just been relatively recently discovered, but there's already a huge investment from the private side of things into this technology. So people are trying to think about how we can use RNA interference through the molecules being siRNA. But front and center is how do we deliver double-stranded RNA in this case as an actual drug. There are two broad strategies by which you can deliver any of these three nucleic acid drugs. Steve went over viral delivery, an example of viral delivery, and then the other broad category is non-viral delivery. And there are a lot of advantages and disadvantages to both approaches. Both are potentially viable at this point in our evolution of tissue regeneration and tissue engineering. And so within the context of within the context of tissue engineering, what we're talking about are coming up with strategies to incorporate these nucleic acid delivery agents into scaffolds. And again, that has been done with both viral delivery and non-viral delivery. There are so many options available here. But again, the broad categories fall into viral delivery versus non-viral delivery. The simplest non-viral delivery technique is to use bare DNA. And this, in fact, has been done, and it's been the basis for startup companies. I would say most of the effort in current investment is in synthetic vehicles, and this is where I'm going to focus today. There's likewise an entire field of different types of viruses that can be used to deliver, and I'm just not going to focus on that. From the standpoint of delivery, this is where the big challenges are, is to see if we can raise up our level of efficiency with non-viral delivery systems to anything approaching the efficiency of biology. And so let me start with gene delivery, although this also is a strategy for delivering antisense and siRNA, and that is with the most basic form of these drugs, which is a plasmid. And I'm not going to go into the biology of this, that's sort of for other people, I guess, to cover, but there really is a lot of design and biology that goes into the design of the plasmid. And while the gene is probably the part that you would think about as the drug, the details of the plasmid construct are very important. And so they usually contain a promoter, the actual gene of interest, and an antibiotic resistance gene. But there's been really huge advances that come from the molecular biology side of things in preparing enhancer-specific promoters for longer-term expression and for tissue-specific expression. And I don't want to gloss over that. It's just sort of outside the scope of this talk. What I'm going to be talking about is once you have in hand the right construct, how can we more efficiently deliver that construct? The reason why this is such a challenge from a drug delivery perspective is that there are barriers that go across the whole organism down to the details of intracellular trafficking. And at all levels, there are significant barriers to getting a functional gene to the right place where it can do its action inside the cell. Outside the cell, at the level of the whole organism, there are huge challenges and huge unknowns, really, when we take, for example, a DNA plasmid and put it into either a systemic delivery or a local delivery environment. There are serum components that can bind to DNA, sequester DNA, and this can be either a positive or a negative depending on the details. Sometimes it's a positive to sequester the DNA, it can be protective to the DNA, but it alters then the bioavailability of that plasmid. It affects which cells can pick it up, it affects where it goes even in the body. Likewise, there are nucleases around. This is an obvious problem that can degrade the DNA. When we get down to the level then of getting within target cells, the DNA obviously is going to have to get to the nucleus eventually. But there are many different pathways by which the DNA can be picked up by the cell.